512 is recurrences. And the first definition we have is a functional equation. And a functional equation tells you how various outputs of a function are related. So, for example, if we have, say we have f of x equals 2x, then one functional equation we can have from that would be f of x plus 1 is equal to 2 times f of x. Right? So if you think about what that means, if we have our function is 2 to the input power, then this f of x plus 1 means 2 to the x plus 1 power. And then the 2 times f of x means 2 times 2 to the x, which are equivalent statements. Okay, so it's relating the outputs of the functions, how they relate. Now, one of the most common examples of functional equations are what are known as recurrences, which are basically the recursive models we've been working with. Okay, so special kind of function that tells how the output of a function at an integer n is related to outputs at integers less than 1. And I think of it as it's a recursive formula without base cases. So you're not given, for example, f of 0 is 7. You're just given that bottom line of the recursive formula, where it says 5 times your previous output. So as an example, you might have something like this. F of n equals 3 times your previous output. But it doesn't tell you where to start. It's merely telling you how to get from one output value to the next. So it's a little bit of an incomplete definition as far as the function goes. Two-term recurrence. Two-term recurrence is pretty straightforward. Good word. Recurrence, so you're referring to previous outputs. Two-term, oh, refer to two previous outputs. Okay, just like there was recurrence using the previous two outputs. So the example I gave was f of n equals f of n minus 1 plus f of n minus 2. So I add the previous two outputs together, which if you start with the right base cases leads to the Fibonacci numbers. If you started with different base cases, like let's say you said f of 0 was 7 and f of 1 was 10, you still get a table where this would be true, but it's not going to match the Fibonacci numbers. You see that all right, Katie? I don't know, it looked like you didn't know if you're squinting because you weren't understanding something or couldn't see it, or?
Yeah, once on set is going to make me feel better.
I did that for a long time too, and then I finally got my eyes checked.
I have contacts, but they're starting to get a little dry.
Okay, all right. So, pretty. Well, you finished writing it. If you're done writing, open your books up to 512. Some ways to explore recurrences. The first way gave you was your function modeling language, FML. The second way was the table. Okay, so make a table, see if you get constant differences after a certain point, you have a constant ratio, so on. And then another way to look at it would be to use the graph. If you graph a bunch of known points, does it look like it fits along the quadrant? Does it look like it's cubic solid? And then another way is using your previous method. So what I would like you to do is, if you turn the page, here's an in-class experiment. and they give you 5 recursive formulas. I want you to take 2 minutes, and I want you to come up with the closed form of those recursive models that you can, and then we'll look at them together. Okay? Any problems with the first one? What did you get for the closed form? Yeah. F of n equals, say again? 7n plus 2. Okay, so you've worked with those a lot. You've figured out by now if you're always adding just a constant onto there, the closed form is linear. So you know if your linear functions in the recurrence is going to be just plus the same number every single time. Okay? And then here, when you're multiplying by the same number every time in the recurrence, Jonathan, what did you get for number 2?
7n.
Right, so f of n equals 3 times 7 to the n power. If you have multiplication by the previous outputs, it leads to an exponential function. Okay, so let's look at then the third one. On the third one, it was f of n equals, started off, what was the first output? Say it again? 3. Okay, so 3 if n equals 0, and then it was 4 times f of n minus 1 minus 6. And it's greater than 0. Okay. So I'm looking at this and I'm thinking, okay, let's see, we've got repeated multiplication. So it might be exponential. But I also have this minus a constant every time. So maybe that makes it linear. I'm not really sure what's going on. So let's look at a table. So what I did, you know, first output's 3, and then it was 4 times your previous output minus 6, right? So I took that and I filled it down. All right, so let's start thinking. What's 4 to the 0 power? 1. Okay, so 4 to the 0 power is 1, and then 4 to the first power is 4 squared, 16, 4 cubed, 64. What could we do to all those answers you told me to get the outputs we wanted? Add 2. So just by looking at a table and seeing, oh, okay, I'm repeatedly multiplying by 4, so this might involve 4 to a power. We can come up with it pretty quickly. So if we have our f of n is equal to 4 to the nth power plus 2. And then I heard a group over there, Mason, I think he came up with a rule. Me and Caden were debating it. Caden was saying, well, that doesn't work when you put 3 in. Okay, that's a great way to check it. So you could have that table, and if you have the values, then pick out, I don't know, if you went to n is 10, put 10 in there and see if it matches your table. If it does, you probably had it right. If not, then you know for sure you didn't have it right. Okay. So we have that one.
Where did you get the 2?
Where did I get the 2 from? Looking at it. Like 4 to the 0 is 1, but we wanted 3.
So just
Four.
interpret it.
Yep, just looking at it, okay, I think I might have 4 to a power. And then, okay, if I had just 4 to the power, it's not going to match my table values, but if I added 2 onto each of those, it would match the table values.
So really the only way to truly understand how to do each of these is just to look at each table and just get better at finding the equation.
No,
Really?
not the only way. Okay, you could graph it, you could experiment it, you could do the function modeling language. You could use what you already know. So just the fact that it was 4 times the previous answer, that led me to think it's probably an exponential. The closed form is probably exponential.
Right.
So it wasn't just looking at a table and guessing. It was using what we'd learned to narrow down, I guess, to hone in. Okay. Now this one, number 4. Anybody get number 4? Did anybody make a table? Okay, so let's look at. Okay, so let's go back, and if we look at the table, all right, I set these up where I didn't put the base cases in. But as you can see, if I click here, we have 5 times our previous output minus 6 times our next output. Okay, so what did we start? We started with 1, then 3, was it?
Yep.
1, then 3. Can anybody tell me what the function is now? Right, 3 to the end. Just by making a table, this one jumped out at us. Is times 3, times 3, times 3, times 3, times 3, so on. The table made this one a lot easier to do. So using a table, we see f of n equals 3 to the n power. And again, just by looking at the table, it jumped out at us. Now they're not all going to be that simple. In fact, the next one is not. So that was the first one. And now number 5. Same recurrence, correct? Same connection between consecutive inputs. Mason, what was on number 5, what was the output when the input's 0?
2.
2? Okay. And then the output when the input was 1 is 5. Okay. Boy, I don't see a constant ratio there. Okay. Now, if we looked at these numbers, see how they're growing quickly? You start jumping up significantly more as we go through, right? Okay, so that's an indication possibly it's exponential. The other way you might know it's exponential is you're multiplying your previous outputs by a number. So that's where we're going to start as our